All right, so now let's let U equal nj uj and del U equal ni. Right? So you remember, this is exactly what we did in the weighted integral statement, right? We assumed approximation for U. Right? Now back then we didn't really, we just sort of assumed the approximations, they were sort of arbitrary, right? We assumed approximation for U, and then we chose the del U to be linear independent, right? 3 linear independent things, or how many ever. And so in this case, we're going to choose them to be exactly the shape functions. Okay, and this is called an Aglerkin approximation. So we have a very systematic approach. We have a 3-step process to develop the weak form. We know how to interpolate with Lagrange polynomials, right? We know how to construct them. So we know how to get the ends. And then we just plug those 2 things into our weak form, and we have the finite element model. So let's write down for I equal to 1, we'll have this equation. Right? And I could go on and write the rest of them, but I'll just write the nth equation. So for I equal to n, now I have that d dx nj uj. Nj is a function of x, right? It's our interpolating function. So I have to, if I take the product rule, then it's d dx uj, d dx nj times uj plus nj times d dx uj, right? Well, what's d dx uj? Uj is what we're solving for, so it's an unknown coefficient. It's a constant, right? It's an unknown constant that we're solving for. So it doesn't zero, right? The derivative is 0. So in this term, I'll just go ahead and write that out. I have nj All right. Therefore, for the ith equation, so everybody see that the I is the index that's going to give you the number of equations, right? The j is a summation, right? So that's, the j is repeated, so that's a summation. And the u equals nj uj, that's a summation. But so then there, so that goes away when I plug it in because it's a summation. You just expand it. But then there's still one free indice. Remember, going back to talk about conditional notation, there's still one free indice. And so that means that if they're free indices, those are the number of equations. Right? So there's I equations. So for the ith equation, we have now I've pulled the unknown coefficient uj out here, right? Just a constant, so I can pull it outside the integral. Okay. So can anyone tell me what happened to my summation of this thing? What happened here for the ith equation? Yeah. So for the ith equation, I would have n I xj. But our shape functions, if we're using Lagrange polynomials, which I'm assuming we are, we're talking about the standard finite element method here, has what? Right? It has a Kronecker delta property, right? So if I equal to j, it's just 1, and otherwise it's I not equal to j, it's 0. Right? So therefore, it's just 1 times qi, otherwise it's 0. Okay? So if we look at what these guys are, we're going to give this thing a name. Well, you can clearly see it's just our bilinear operator with the values n, I, and nj plugged in. And then if you call this maybe fi, so you'd have fi minus qi of 0. Okay. And then a lot of times, especially in mechanics, we'll write this thing as kij, uj, and then if we call this whole thing fi, now we just have a matrix equation to solve. So this thing typically from its roots in mechanics is called a stiffness matrix. So even in other disciplines, because the finite element method sort of history was founded in matrix methods in mechanics, right? That's sort of a name that's stuck. So we call this the stiffness matrix, even sometimes when we're talking about diffusion or heat diffusion or temperature diffusion or anything else, right? And of course, the solution to that is just this. So let's